Welcome back to the Deep Dive, where we take those sources you give us and really try to pull out the cool stuff.
That's right. We try to find those hidden gems.
And today we're deep diving into something we all experience every single day, gravity.
It might seem kind of ordinary,
Yeah.
But trust me, there's way more to gravity than you might think.
Okay, I'm interested. We all know what gravity does, right?
Yeah.
Things fall down.
Yeah.
But why?
Yeah.
What's the bigger picture?
Well, it all starts with the idea that, every object in the universe
Okay.
attracts every other object with a force.
Okay.
And that force is, you guessed it, gravity.
So to be clear, you're saying my coffee mug right here is pulling on the earth.
Yes.
And the earth is pulling on my coffee mug.
That's exactly it. It's a mutual attraction. It's like they're having a little tug of war.
Uh-huh.
And it was Newton, Sir Isaac Newton, who really figured this whole thing out.
Okay.
With his law of universal gravitation.
Universal gravitation.
Meaning it applies everywhere.
So it's not just here on Earth, it's everywhere.
Everywhere in the universe.
Wow.
Yeah.
That's incredible. But hold on, if everything's pulling on everything else, why don't we all just clump together into a giant messy ball?
That's a great question. And it's something that a lot of people kind of wonder about.
Yeah.
And the answer is that the strength of that pull depends on a couple of things.
Okay.
Mass and distance.
Okay.
So more massive objects, they have a stronger gravitational pull.
Like the sun has a stronger pull than, say, my coffee mug.
Exactly. And then the farther apart two objects are, the weaker that force gets between them.
Okay, so bigger objects have a stronger pull, more mass equals stronger pull.
Yes.
And distance weakens the pull. Makes sense. But how much weaker? If I move twice as far away from something, is the pull half as strong?
That's a good guess, but it's not quite that simple. It actually gets weaker much, much faster than that. It follows something we call the inverse square law.
Inverse square law. You're going to have to break that down for me.
Sure, no problem. It's really not as complicated as it sounds. Think of it this way. Imagine a light bulb. The farther you move away from the light bulb, the dimmer it looks, right?
Yeah, obviously.
But it's not just a simple relationship where if you double the distance, the light is half as bright.
Oh, okay.
It's actually only 1/4 as bright.
So the brightness drops off more quickly the farther away you get.
Yes, exactly.
Okay.
And gravity works in a very similar way. If you double the distance between two objects, the gravitational force between them becomes 4 times weaker. If you triple the distance, it becomes 9 times weaker, and so on and so on.
Okay, so it's not a one-to-one thing. It's the farther away you get, the weaker it gets much faster.
Exactly.
Okay, so that's why we're not all just being sucked toward the most massive thing in the universe, right?
That's exactly right.
Because the distance weakens the pull so much.
It weakens it so much that the pull from, super distant objects is just negligible.
That makes a lot of sense. Okay, so we've got this universal force, this gravity.
Yes.
It's weaker the farther away you get.
Yeah.
What about stuff that's already in motion?
Right.
Like the moon going around the Earth.
Yes. Yeah.
How does that work with gravity?
That is where things get really interesting. Imagine you're throwing a ball, right?
Okay.
It naturally wants to just keep going in a straight line.
Unless it hits something like my window.
Right, exactly. Well, the same principle applies to the moon. It wants to just zoom off in a straight line. But the Earth's gravity, it acts like a tether, an invisible tether that's constantly pulling it inwards.
So it's the moon is always trying to escape, but Earth's gravity keeps reeling it back in.
That's a perfect way to put it.
Huh.
And because the moon is also moving sideways, that constant tug of war results in it going around in a circle, an orbit.
Okay, so it's that sideways motion plus the Earth's gravity creates that circular orbit.
Exactly. It's this delicate balance between the moon's inertia. Yeah. Inertia, which is, that tendency to just keep moving in a straight line.
Okay.
And the inward pull of gravity.
Okay, that's pretty wild.
Yeah.
So it's not just gravity, it's gravity plus that inertia, that sideways motion that keeps the moon from flying off into space.
That's a great way to think about it. It's like a cosmic dance,
Mind blown. Seriously. Okay, I need a second to process all of this.
Yeah.
So gravity is not just about things falling down, it's also about keeping things in orbit. It's about this cosmic dance.
Yeah.
But okay, if the Earth is pulling on the moon, shouldn't the moon also be pulling on the Earth?
Ah,
Isn't gravity like, a two-way street?
It absolutely is. It always goes both ways.
Okay.
And Newton's third law of motion, it tells us that for every action, there's an equal and opposite reaction.
Right.
So just as the Earth is pulling on the moon is pulling back on the Earth with the same force.
Okay, so why don't we see the Earth like, going crazy, like bounce around because of the moon's pull?
Right. That's a great question. And it brings us to Newton's second law of motion.
Okay, we're on a roll with Newton's laws.
We are. And this law basically tells us that the acceleration of an object, how quickly it speeds up, right,
Okay.
is directly proportional to the force that's applied to it and inversely proportional to its mass.
So you mean like bigger objects are harder to move, even if you're using the same amount of force?
Exactly. That's a great way to put it. The Earth is much, much more massive than the moon. So even though they're pulling on each other with the same force, the Earth's acceleration is tiny.
So it's like trying to push a car versus a bicycle.
Exactly. You'll have a much easier time moving that bicycle.
So the Earth does move a little bit because of the moon's pull, but it's so tiny that we don't even notice it.
Yes. They both actually orbit around a common center of mass.
Okay.
But that center of mass is much closer to the Earth's center.
Right, because the Earth is bigger.
Exactly.
Wow, that's incredible. It's amazing how these simple concepts can actually lead to some pretty complex stuff.
It really is.
Okay, so we've covered a lot of ground here. Gravity, mass, distance, Newton's laws of motion.
We have.
But there's one thing that I keep thinking about. We've talked about how gravity is this universal force, but why don't we see things just flying toward each other all the time?
Right.
I mean, if everything's pulling on everything else, shouldn't my pen, be attracted to me right now?
That's a really smart observation. And it gets to the heart of how weak gravity actually is, especially on a small scale.
Great, weak. But we were just talking about how it holds the moon in orbit.
That's true, but remember, the strength of gravity depends on mass.
Mm-hmm.
You and your pen have very, very little mass compared to planets and stars.
Okay.
So the gravitational force between you two is incredibly tiny.
So the force is there, it's just too small to really make a difference.
Exactly. It's like trying to move a mountain with a feather. The force is technically there, but it's just not strong enough to overcome all the other forces, like friction or the Earth's gravity.
Right. Okay, I get it.
Yeah.
So even though gravity is universal, it's the big players, the massive objects that have the biggest effects.
That's exactly right.
The little things, it's there, but it's not noticeable.
Yes.
Okay, that makes sense. This has been super helpful. Before we move on, can we just quickly define gravity in simple terms?
Sure.
Like something I could explain to my, my niece or nephew.
Absolutely. Gravity, it's a force of attraction between any two objects that have mass. The more mass those objects have, the stronger the attraction. And the farther apart they are, the weaker the attraction.
Perfect. Okay, I think I'm ready to keep exploring. What other cool concepts are related to this force?
Well, we've talked about how gravity pulls things down, but have you ever thought about why some things actually float?
Ooh, that's a good question. Why does a boat made of metal float?
Right.
But a metal coin sinks?
Right.
I don't know. That's always confused me.
Yeah.
I mean, they're both metal.
Right. That's where the idea of buoyancy comes in.
Right.
It's an upward force that fluids exert that opposes the weight of an immersed object.
Okay.
So when you're in a swimming pool and you feel lighter, that's buoyancy pushing up on you.
Okay, so the water is pushing back against gravity a little bit.
Yeah, exactly. The water is pushing up on you with a force that is partially counteracting the force of gravity pulling you down.
Okay, but why do some things float and others sink?
That's a great question. And it all comes down to density.
Density.
Density is a measure of how much mass is packed into a given volume.
So something that's really heavy but spread out over a large area, like a giant inflatable raft, would be less dense than a tiny pebble.
Exactly. And here's the key. Objects that are less dense than the fluid they're in will float, whereas objects that are denser than the fluid will sink. So a boat floats because its overall density, including all the air inside it, is less than the density of water.
Okay.
Whereas a metal coin, its density is much higher than water, so it sinks.
So buoyancy is all about the upward push of a fluid.
Yes.
And whether something floats or sinks depends on how its density compares to the fluid.
Exactly.
Okay, I'm following you. So we've got this upward push from the fluid, and that's buoyancy.
Yes.
But hold on. how do we actually figure out how strong that force is? Like, is there a way to calculate it?
Absolutely.
Okay.
And for that, we can thank the brilliant mind of Archimedes.
Archimedes, wasn't he the guy who, like, ran through the streets shouting, Eureka?
That's the one. And the principle that he discovered, is called, well, Archimedes' principle.
That's pretty convenient.
It is.
All right, what does Archimedes' principle tell us?
Well, it says that the buoyant force on an object that's submerged in a fluid is equal to the weight of the fluid that is displaced by the object.
Wait, so if I jump in a bathtub full of water and some spills over, the weight of that spilled water is the same as the buoyant force pushing up on me.
That's exactly the idea. The more water you displace, the greater the buoyant force acting on you. And the story goes that Archimedes actually figured this out while taking a bath, hence the famous Eureka moment.
Oh, so that's where that comes from.
Yeah.
Okay, that's a great story, and it makes it so much easier to remember.
It does.
So this principle, you're saying, can be used to calculate the buoyant force on any object in any fluid.
Yes, it's a fundamental principle. It helps us understand why ships float, how submarines are able to dive, even how hot air balloons are able to rise.
So it's not just some, like, theoretical thing.
Mm-hmm.
It actually has real-world applications.
Oh, absolutely. It's a testament to how understanding these fundamental principles of physics can lead to, practical solutions and all sorts of technological advancements.
Yes, it's incredible. We've gone from dropping feathers and hammers to understanding why ships float, all thanks to gravity.
It is amazing, isn't it?
It is. It's amazing how much there is to learn about gravity and how it affects, everything around us.
It really is. And you know what? We've only just scratched the surface. There's so much more to explore.
Oh, there is?
Oh, yeah. Things like black holes or even how gravity can affect time itself.
Wait, gravity affects time. Now, that's something I definitely want to hear more about.
Oh, yeah. We'll get into that.
Yeah.
So we've been talking about how gravity affects things, on a grand scale, like planets and moons and all that.
Yeah.
But what about here on Earth?
Uh-huh.
Like, how does gravity shape our everyday experiences?
Yeah, that's a good point. We know gravity pulls everything down.
Right.
But why do things fall at different speeds? Like, if I drop a feather and a hammer, the hammer will hit the ground first, right?
Yeah, that's a classic question. And the answer has to do with air resistance.
Okay. Air resistance. So, like, the air is pushing back against things as they fall.
That's exactly it. It's like a kind of friction that the air creates. That opposes the motion of the objects. It's like trying to run through a swimming pool. It's much harder than running on land because the water creates more resistance.
Right, yeah. So the feather is more affected by air resistance because it's lighter and has, like, more surface area.
Exactly. The hammer, being more compact and dense, cuts through the air more easily.
So if we were to drop a feather and a hammer in a vacuum where there's no air, they would fall at the same rate.
That is exactly right. And this was famously demonstrated, or at least so the story goes, by Galilei. He supposedly dropped objects from the Leaning Tower of Pisa.
Oh, right, to prove this point.
Exactly.
That's a pretty cool story. Whether or not it actually happened, the idea is still fascinating. So in a vacuum, everything falls at the same rate no matter its mass or shape.
Yes, precisely.
Yeah.
And the rate at which objects fall in a vacuum is determined by something called the acceleration due to gravity.
Okay.
Often just shortened to g.
Acceleration due to gravity.
Mm-hmm.
So it's not just a constant pull, but things actually speed up as they fall.
Yes, they do. The acceleration due to gravity is constant near the Earth's surface, and it's about 9.8 meters per second squared.
Okay.
Which means that for every second an object falls, its speed increases by 9.8 meters per second.
Wow, that's pretty fast. So if something falls for like 2 seconds, it'll be going almost 20 meters per second.
That's right. And we can actually use equations of motion to calculate exactly how fast an object will be falling, how far it will have fallen, and how long it will take to hit the ground, as long as we know its initial velocity, of course.
Okay, this is starting to sound a little bit like physics class, but I'm still with you.
It's all connected.
Yeah. So we've got this air resistance affecting how things fall.
Right.
And then we've got this acceleration due to gravity making things speed up as they fall. Is there a simple way to define, like, what free fall is?
Sure. Free fall is simply the motion of an object under the sole influence of gravity.
Yeah.
In other words, it's when the only force acting on an object is gravity.
So like a feather floating down to Earth in a vacuum, that would be considered free fall.
Precisely. But even here on Earth, we can observe free fall, even if it's not perfect. Like, imagine dropping a ball It's in free fall until it hits the ground, even though there's some air resistance.
Right, right. Okay, so we've got free fall figured out. Now, something I've always been a bit confused about. Mass and weight. Are those the same thing?
That's a great question, and it's something a lot of people get mixed up. Mass and weight, they're related, but they're not the same thing.
Okay, so break it down for me. What's the difference?
So mass is a measure of how much matter an object contains. It's a fundamental property of the object, and it doesn't change no matter where the object is.
So my mass is the same whether I'm on Earth, on the moon, or floating out in space.
That's right. Weight, on the other hand, is a measure of the force of gravity acting on an object.
Okay, so my weight can change depending on where I am. Like I would weigh less on the moon because the moon's gravity is weaker.
Exactly. Weight is directly proportional to the gravitational field you're in.
Okay.
On the moon, your mass would be the same,
Right.
but you would weigh about 1/6 of what you weigh on Earth.
Okay, I think I'm getting it. So mass is about the amount of stuff in an object, and weight is about how strongly gravity's pulling on that stuff.
That's a perfect way to put it. So to summarize, mass is a fundamental property of an object. It measures its resistance to acceleration, and it remains constant regardless of location. Weight, on the other hand, is the force with which gravity pulls on an object, and it varies depending on the gravitational field.
Okay, that's really helpful. I think I finally get the difference between mass and weight. All right, let's keep going with this gravity deep dive. What other interesting concepts are related to this force?
Well, we've talked
Yep.
about how gravity pulls things down, but have you ever wondered why some things float?
Yeah, like why a boat made of metal can float, but a metal coin sinks.
Right, that's where the concept of buoyancy comes in. It's an upward force exerted by a fluid
Okay.
that opposes the weight of an immersed object.
So when I'm in a swimming pool and I feel lighter, that's buoyancy pushing me up.
Exactly. The water is pushing up on you with a force that partially counteracts the force of gravity pulling you down.
Okay, so it's like a little underwater battle between gravity and buoyancy.
Kind of, yeah.
But why do some things win that battle and float while others sink?
You know, that's the big question, and it all boils down to density. Density is a measure of how much mass is packed into a given volume.
So like something really heavy but spread out over a large area like a giant inflatable raft would be less dense than a tiny pebble.
Exactly. And here's the key. Objects less dense than the fluid they're in will float, while objects denser than the fluid will sink.
Okay, so a boat floats because its overall density, including the air inside it, is less than the density of the water.
Exactly. You got it.
And a metal coin sinks because it's way denser than water.
Exactly. That's exactly right.
Okay, that makes sense. So buoyancy is all about this upward push from a fluid, and whether something floats or sinks all comes down to its density compared to the fluid.
That's a great summary. So to define buoyancy really concisely, it's an upward force exerted by a fluid that opposes the weight of an immersed object, and that force is dependent on the density of both the object and the fluid.
This is great. We're really starting to get a good understanding of how gravity and all these other forces work together. But hold on a sec. How do we actually figure out how strong that buoyant force is? Like, can we calculate it?
Absolutely. And for that, we have to thank the brilliant mind of Archimedes.
Archimedes, the Eureka guy.
That's him. And fittingly, the principle he discovered is called Archimedes' principle.
Okay, I'm intrigued. What does this Archimedes principle tell us?
It states that the buoyant force on an object submerged in a fluid is equal to the weight of the fluid displaced by the object.
Hold on, are you saying that if I jump into a bathtub that's full of water and some spills over the edge, the weight of that spilled water is the same as the buoyant force pushing up on me?
That's exactly the idea. The more water you displace, the greater the buoyant force. And legend has it that Archimedes actually figured this out while taking a bath, hence the whole Eureka moment.
Oh, that's where that came from.
Yeah.
That's amazing. It makes the principle so much easier to visualize and remember, so we can use this principle to calculate the buoyant force on any object in any fluid.
Precisely. It's a fundamental principle that applies everywhere. It helps us understand why ships float, how submarines dive, even how hot air balloons rise.
Wow. So Archimedes' principle isn't just some theoretical idea. It has real-world applications that affect us every day.
Exactly. It just goes to show how understanding these fundamental principles of physics can lead to real practical solutions and all kinds of technological advancements.
This is mind-blowing. We've gone from dropping feathers and hammers to figuring out why ships float. It's amazing how much there is to learn about gravity and how it affects the world around us.
It really is. And you know what? We've only just scratched the surface. There's so much more to explore, from the mysteries of black holes to the strange effects of gravity on time itself.
Wait, gravity affects time. Now that's something I have to hear more about.
Yeah, we haven't even touched on some of the, like, really mind-bending parts of gravity.
Okay, like what?
Well, like how it's connected to time.
Okay, you've got my attention. Tell me more about how gravity affects time.
All right, well, to get that, we kind of have to talk about one of Einstein's biggest ideas,
Okay.
the theory of general relativity.
Einstein relativity. Those are some big words. Are we going to get into like really complicated physics here?
No, don't worry, I'll keep it pretty simple.
Okay, good.
Basically, Einstein's theory says that gravity isn't just a force, like how we've been talking about it so far. It's
Right.
actually like a warping of space-time itself.
Hold on, warping space-time. What does that even mean?
Okay, imagine a bowling ball, right? Sitting on a trampoline. The bowling ball makes a dip, right? A dent in the trampoline surface.
Yeah, I can picture that.
Well, Einstein said that massive objects like planets and stars do the same thing to space-time.
Whoa, okay.
They make a dent, a curvature in the fabric of space and time.
Okay, so gravity isn't a force pulling things down. It's like a warping of space and time.
Yeah, that's the idea.
That is a lot to process.
It is. But think of it this way. If you roll a marble across that trampoline, it's going to curve around the bowling ball, right?
Yeah.
It's not that the bowling ball is pulling it. The marble is just following the shape of the trampoline.
Okay, I think I'm starting to see how that analogy works.
Mm-hmm.
So objects are drawn toward each other, not because of a force, but because they're following these curves in space-time.
Exactly. And here's the really crazy part. One of the results of this warping of space-time is that time actually slows down.
Really?
Yeah.
It slows down.
Yeah, in stronger gravitational fields.
Wait, are you telling me that time can actually slow down?
That's right. It's called gravitational time dilation.
Gravitational time dilation.
The stronger the gravity, the slower time passes compared to, a weaker gravitational field.
So, like, if I was hanging out near a black hole, which has super strong gravity, time would move slower for me than for someone back here on Earth.
Theoretically, yes.
So that'd basically be time traveling.
Yeah, in a way.
Whoa.
Although actually getting to a black hole and back is a whole other issue.
Right.
But even here on Earth, we see these tiny little effects of time dilation.
Really?
Yeah, time actually passes a tiny bit slower at sea level than it does on a mountaintop.
It does.
Yeah, because gravity is a little stronger at sea level.
Wow, so time isn't absolute, it's relative.
Exactly.
And it's affected by gravity.
Yes.
Okay, my mind is officially blown. This is incredible. So, okay, you mentioned black holes. What exactly is a black hole?
A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape.
Wow.
Imagine that bowling ball on the trampoline got so heavy that it just rips a hole right through the fabric.
Yikes. Okay, so anything that gets too close to a black hole, it's just gone.
Pretty much. Once you cross the event horizon, that point of no return, there's no coming back. Even light gets trapped inside.
So we can't actually see a black hole directly, right?
Yeah.
Because no light can get out.
Exactly. We can only detect them indirectly by, observing how they affect the stuff around them. Like, if a black hole is orbiting a star, we can see how the star's motion is messed up by the black hole's gravity.
So it's kind of like detective work where you're figuring out that something invisible is there because of how it's affecting the things around it.
That's a perfect way to describe it.
Yeah.
And actually, in 2019, the Event Horizon Telescope, it managed to capture the first ever image of a black hole's shadow.
Really?
Yeah. Which gave even more proof that they really exist.
That's amazing. So black holes are these extreme places where gravity is just, like, king.
Yes.
But what about the opposite? What about, like, those vast empty spaces between galaxies? Yeah.
Is there gravity there too?
That's a great question. And the answer is yes, gravity is everywhere.
It is.
Yeah. Even in those seemingly empty parts of space, it's just that in those regions, the forces are much, much weaker because there's less mass.
So even in the emptiest parts of the universe, gravity's still at play, just subtly influencing how galaxies and everything else moves around.
That's exactly right. Gravity's reach is basically infinite.
Wow.
It's the force that holds the entire universe together, shapes its structure, its evolution.
This deep dive into gravity has been incredible. It really makes you realize just how vast and complex the universe is and how much we still don't know.
It really is humbling, isn't it?
Uh-huh.
It's a reminder that we're only a tiny part of something so much bigger and more mysterious than we can even imagine.
But that's what makes it so exciting, right? There's always something new to discover, always another layer to uncover.
Exactly. The universe is this endless frontier full of wonder and so much to explore. And gravity, it's one of the key forces that's guiding us on this journey of discovery. This has been an amazing journey. We've gone from simple stuff like mass and weight to mind-blowing concepts like general relativity and black holes. I feel like I have a completely new understanding of this fundamental force.
It's been a pleasure exploring all of this with you. And remember, next time you see an apple fall or you look up at the night sky, think about that invisible force that connects it all: gravity.
That's a beautiful thought. Thanks for joining us on this deep dive into gravity. Until next time, keep exploring the world with curiosity and a thirst for knowledge.